Hello everyone. In this video, I'll discuss about the derivation of electric field due to another type of line charge, which is circular ring of charge. We'll follow these general steps which we discussed in earlier videos to find electric field intensity due to uniform continuous charge distributions for our circular ring problem statement also. The problem statement goes here. The circular ring of charge contains uniform charge density of rho L coulomb per meter, where the ring radius is A and is located on z equal to 0 plane with its axis as z-axis. The estimation of electric field intensity is at point P lying along z-axis. We can give the graphical representation as such, with the circular ring lying on z equal to 0 plane and radius of A with axis as z-axis will have center at origin. And the observation point P is along z-axis. Here we are considering at a height of h along z-axis, giving the coordinates of point P as 0, 0, h. We'll solve the problem in cylindrical system, considering a differential length element along the circular ring of charge. In general, cylindrical system will have the differential length element in rho direction as d rho, phi direction as rho d phi, and z direction as dz. In our case, radius is constant, which is A of the circular ring, and the ring is lying on z equal to 0 plane, where z is also constant. Leaving these d rho and dz component, the variable component is only phi here, with the range of phi from 0 to 2 pi. With this, the differential element will be only the phi component, which is rho d phi. In our case, rho value is equal to A. We can write the differential length element as A d phi. From this, we can estimate the total charge contained in the small length element dl as dq, which is rho l times the length. Here, the length is A d phi. We have to find the displacement vector from this small differential length element carrying a charge of dq to the point P. We have to fix the coordinates of dl and the point P. dl is considered at angle of 0 and at a radius of A on z equal to 0 plane, giving the coordinates as A0, 0. This angle is same as the angle of point P, because when we look at the point P from any point along the circular ring, it has symmetry about the axis. That is, when we go around with the same radius and at the same height with different angles, the point P appears to be same or symmetric. Thereby, the resultant vector r, or the displacement, will have only radial component and z component. Phi component will not be there. We can write the vector r as minus a in rho direction plus h in z direction. And thereby we can compute magnitude of this r and substitute in the formula for electric field intensity from Coulomb's law. So the differential amount of electric field intensity due to the differential length element can be written in terms of differential charge dq and the displacement vector r divided by magnitude of r cube. Substituting all these into this expression, we'll get the differential amount of electric field intensity expression as rho L into A d phi in place of dq, and in place of vector r, we have minus A rho plus h az, and in place of r cube, we have a square plus h square the whole power 3 by 2. We have to integrate this dE over the entire range of phi to get the total electric field intensity due to the circular ring at the point P. This line integration is with respect to the variable phi. Before performing the integration, we have to consider the radial symmetry about the axis. That is, when we consider the point P, that is the observation point P along the axis of the circular ring, the contribution of smallest electric field intensity vectors everywhere throughout the circular ring will have resultant only in z direction. That is, for every d L component on the circular ring, there will be exactly diametrically opposite element cancelling the radial components, resulting in only z direction component of the total electric field intensity vector. This can be justified with the parallelogram law of addition between two vectors. If I consider two vectors A and B forming the two sides of the parallelogram, the resultant of addition of the two vectors will be in or along the diagonal of this parallelogram. Now, if I consider the differential length element and its diametrically opposite element on the same plane, the addition of these two components will have resultant only in z direction. Likewise, infinite number of such differential length elements will contribute together to get the total electric field intensity, which is obtained by performing the integration about the entire circular ring. We can say this as the radial symmetry about axis of the circular ring, where the radial components will cancel, only z direction component will be resulting. So neglecting this radial component, considering only the z component, we can write the expression for electric field intensity for integration as rho L times A d phi into H A z, which is the z component, divided by 4 pi epsilon into A square plus H square, the whole power 3 by 2. The variable of integration is phi. Integrating with respect to phi, we can get 2 pi as the resultant, which is cancelling with 4 pi in the denominator to give 2 in the denominator. The expression for electric field intensity due to circular ring of charge can be given as rho L A H by 2 epsilon into A square plus H square the whole power 3 by 2 in z direction with the unit as volt per meter. Thank you for watching the video.